Editorial is a presentation about AVL trees. Before going into the concept of AVL tree, let's discover why the concept of AVL tree came into existence. Binary tree. A binary tree is a tree where the parent node consists of at most two children. That means either 0, 1 or 2. The thing we need to keep in mind is there will be no proper order for inserting elements in a binary tree. If there is no such proper order for inserting elements in a binary tree, then definitely it's gonna be difficult to search an element in a binary tree. Its time complexity exceeds in this case. The need of tree operations to be performed becomes more difficult in case of binary tree because of its complexity. Because of such complexities occurring in binary tree, here comes the concept of binary search tree. It has a very particular order of inserting elements, where the root node must be greater than the left subtree and the root node must be less than the right subtree. Now all the operations here becomes easy. But there's a scenario which may think about AVL tree, and that is left skew tree and right skew tree. In the case of left skew tree and right skew tree, the height of tree is n. Hence, the complexity to search thereby becomes big O of n. The same for deletion and insertion. Now, this generally occurs due to the missing of a factor, and that factor is our balance factor. Balance factor here is defined as the height of left subtree minus the height of right subtree. If we observe the binary search tree given here, the height of left subtree is 1, 2 and 3. The height of right subtree is 1, 2, 3 and 4. So the difference between the height of left subtree and right subtree here is minus 1. The same is calculated for each and every node of this tree. If we observe here, the balance factor of this node is 2 and this node is minus 2, which is not acceptable, and such cases are said to be imbalanced. Hence this is an imbalanced binary search tree. If the binary search tree is balanced as in mentioned above, then such tree is considered as an AVL tree. And if the binary search tree consists of any such unambiguous balance factors, then it is said to be an imbalanced binary search tree or not an AVL tree. Hence, we can define the AVL tree as a self-balanced binary search tree. So, here the height of an AVL tree is log n, hence the search time of an AVL tree is log n. So, all other operations of AVL tree becomes easy. Now, let's look at this Venn diagram. This Venn diagram states two important points about the relation between AVL tree, binary search tree and binary tree. The first important point is all binary search trees are binary trees, but all binary trees may or may not be binary search trees. And the second important point is all AVL trees are binary search trees, but all binary search trees may or may not be AVL trees. Now here comes the concept of rotations in AVL tree. Basically, the rotations in AVL tree takes place if there is any imbalance in binary search tree. Imbalance in binary search tree occurs if there is neither 0 nor minus 1 nor plus 1 as a balance factor in a binary search tree. So in those cases we will perform the rotations in AVL tree. So one such rotation is RR rotation. As mentioned in this example, there are three elements 8, 9, 10 which are arranged in the form of a binary search tree. If you observe here, the balance factor of the root node 8 is minus 2, which is not acceptable for an AVL tree. In order to convert this imbalanced binary search tree to a balanced binary search tree, we have made one anti-clockwise rotation so that we have obtained this binary search tree. Now if we observe the balance factor of this binary search tree, it is 1 minus 1, which is 0, and even same with the leaf nodes, its balance factor is 0. hence it satisfies the principle of an AVL tree. So it is called as an AVL tree. Now the second such rotation is LL rotation. Here we have taken an example of three elements 10, 9, 8 which are arranged in a binary search tree fashion. If we observe the balance factor of the root node 10, it is 2 minus 0, which is 2, and is not acceptable, hence it is an imbalanced binary search tree or not an AVL tree. In order to convert this non-AVL tree to an AVL tree, we need to make one clockwise rotation so that the final obtained tree will be 9, 8 and 10. If we observe the balance factor of this root node 9, it is 1 minus 1, which is equal to 0, and the same with the leaf nodes. Hence the process and the principle of the AVL tree is satisfied. Now moving on to RL rotation. If we take an example of 10, 12 and 11, they are arranged in the following format which satisfies the principle of binary search tree. Now this, if we observe here, the root node 10, its balance factor is not acceptable because the height of left subtree is 0 and the height of right subtree is 2, which is equal to 2. So it is an imbalanced binary search tree. So in order to convert this imbalanced binary search tree to an AVL tree, here there are two steps which are needed to follow. The first step is to convert the RL format to RR format. So here the RL format is being converted to RR, which made to form this binary search tree. Now let's see whether this satisfies the principle of AVL tree or not. If you observe the root node, the height of left subtree is 0 and the height of right subtree is 2, which is not still acceptable. So this tree structure is familiar to the first condition that we have seen earlier. So we need to perform the LL rotation here. So this becomes 11, 10 and 12. Hence this is a balanced binary search tree. Now moving on to LR rotation. Here we have taken an example of 10, 8 and 9 which are arranged in a binary search tree format. So if we make the LR to LL rotation and then we follow the RR rotation, then it's easy to make this imbalanced binary search tree to a balanced binary search tree which satisfies the properties of AVL tree. Hence this is a balanced binary search tree and an AVL tree. So these are the four rotations that are made to convert the imbalanced binary search tree or non-AVL trees to acquire the properties of an AVL tree. Thank you.